Hello, everyone.
Oh. Hello.
Can you hear me? Everything is okay?
Yes.
Yeah.
Wonderful. There are only 8 of us as yet, so let's wait. Not so many. How is the situation in Annapolis? Everything is fine?
Everything is the same.
Okay, the same, yes. The same doesn't necessarily mean fine, right?
Right.
Why so pessimistic?
Because of online learning.
Oh, so you do not like online learning.
Yeah. Yes.
Okay, let's discuss that, by the way, so maybe we can improve something. So what is difficult? Let's say the whiteboard in online learning is difficult to comprehend, or maybe less opportunities to ask questions, or what? Or maybe it's more about labs, not lectures. So please say, because you know, it's unfortunately it is a reality. This pandemic we have to live with, but we can improve our online learning. So what is particularly bad?
The worst thing is sitting behind your computer all the time. All other things are well. The whiteboard, asking questions, labs, all are okay.
Okay, so it is just tedious to sit. No social interaction, just sitting glued to the computer screen. Do I understand that?
Yeah, that was I meant.
Okay,
What?
okay. So yes, you know, it's a psychological stress, by the way. And there are some reports which I personally do not completely agree with, but there are even some medical reports which say that the stress and depression and all those, you know, bad things caused by isolation at home may have done more harm than the pandemic itself. So, or we're joining. Okay, so this might be. But by the way, as far as I understand, we do have a psychologist in Napolis. So in case of any problems, if it becomes really hard, you can consult with that psychologist, or there are some others operating remotely and available on our, you know, services in Annapolis Telegram channel. So if worst comes to worst, then even professional help can be sought, but I fully understand you. Okay, still only 19 of us out of roughly 60 expected. So let's wait further. Why are we so slow to join?
I think some people can't find the link.
Can't find the link. I will publish the link again. Although it is just 2 messages up. 1 second. Oh, publish link on Zoom itself? Yes, of course, it is a recurring meeting. So all details are the same, always the same. So what I will do is probably, well, publishing it in Zoom is probably counterproductive because you can't see it unless you actually join Zoom. But I will publish it on Telegram. It is always the same. It is the same meeting ID as usual. It is indeed a recurring one. Okay. So now 32 of us, more than 50%. So we can really start. All right. So what we are going to do today? Today we will provide some final concluding remarks about changing coordinates. You remember last time we completed our example with topocentric and geocentric coordinates. Then we introduced the notion of spherical coordinates. For spherical coordinates, we provided transformations both back and forth between spherical and rectangular or Cartesian coordinates. It turned out that going from spherical to Cartesian is very straightforward. Going back is not so straightforward because there are some degenerate cases. So the question is, have you already had labs implementing these Cartesian to spherical transformations in software?
Yes, but there wasn't the same as we discussed in a lecture. Original point wasn't in the center of the sphere, but in the top of the sphere, and it was strange.
In the top of the sphere? So what was in the top of the sphere?
Like the angle which was...
Okay. So the latitude was not from the counted not from the equator but from the pole.
Yes.
That's perfectly okay. You know, this is only a matter of convention. Obviously, sometimes it is easier to do that because then your latitude is from 0 to pi rather than from minus pi over 2 to plus pi over 2, as in our case. So probably just doing from 0 to pi is a little bit more, I wouldn't say more straightforward, but some people may find that it is more conventional, yes. So obviously all those coordinate systems are not uniquely defined. There are so many ways of how they can be defined. And also the longitude in that system was probably not from, in your numerical example, not from 0 to 2 pi, including 0 but not including 2 pi, but probably from minus pi, not inclusive, to plus pi inclusive, or something like that, right?
Mm-hmm.
That's
probably yes.
Sorry?
I said probably yeah, like that.
Yes, like that. So that's perfectly okay. These are just different definitions, and I think it is very good that we did both, because you see how to deal with those subtleties, and that coordinate transform, they do require significant care, in fact. Okay, so now let us do a similar thing. We will consider some final examples, and then from that point on, we'll proceed to very simple yet very important topics in our algebraic geometry. You know what? Defining straight lines in three-dimensional space. Interestingly enough, defining straight lines does require some mathematics, not very much, but it does require something. So we need to pay attention to that. After that, probably, maybe at the end of this lecture, maybe from next lecture on, we will move to planes in three-dimensional space. Then we'll consider various things like intersections between straight lines and planes, planes between themselves. Yes, can you hear me? Sorry, what was the question?
I think it was just noise.
Noise, okay. Intersections between planes and straight lines. And after that, we'll move to more advanced topics like second order curves, but that's not immediate. So we need to work with the geometry of most elementary linear algebra and algebraic geometry objects, such as straight lines and planes first. And believe me, there are quite a few interesting things there, in spite of their apparent geometrical simplicity. So, can you see
Yeah, we
the
can.
whiteboard? Okay.
Yeah.
Let us consider the following example. We have already seen, just to do it again, we have already seen orthogonal transformations in 2D and 3D. Okay, in 2D, suppose that you remember orthogonal transformations can be rotations and symmetries. Okay, rotations are characterized by what? How do we distinguish rotations and symmetries?
Rotation matrix.
Or 2D matrix.
In general, both rotations and symmetries just a second. Both rotations and symmetries are orthogonal transformations, or we can even say orthogonal and normal. Okay, the matrices are orthogonal and normal. What is the difference between them? Between the matrix, a matrix of rotation and a matrix of symmetry?
The second have negative determinant.
Indeed, not just negative, but the determinant by the absolute value is 1 in both cases. Only for rotation, the determinant is equal to +1. For symmetry, the determinant is equal to -1. Okay? Apart from them, the same. So suppose that going back to 2D rotations, in general, they are obviously represented by a 2D matrix, which we again denote by A11, A12, A21, A22. So what can we say about this matrix? We say that, first of all, it is orthogonal. By orthogonality and normal, so we can say that, let's say, either columns or rows, if you remember how we construct this matrix, A11 and A21 are actually components of a new I prime normal vector in the original coordinate system, right? So we can say orthogonality means if these are components of I prime, these are components of J prime, then orthogonality means that obviously these two columns are orthogonal to each other, which means that A11, A12 plus A21, A22 equals to 0. So we're talking about the orthogonality of columns. Normality means that the columns are normal. So A11 square plus A21 square equals to 1. A12 square plus A22 squared equals to 1. So for this matrix, we have 4, in the general case, we have 4 entries, right? And those 4 entries are connected by 3 constraints, all right? So we see 4 entries, 3 constraints, equations. So generically, what does it tell us? It tells us that, in fact, those 4 entries, of those 4 entries, only one is free, correct? So we have only one free parameter here. All right? only one free parameter. Would you agree with that?
Yeah.
Okay. So how do we select this free parameter? We can, for example, select just one matrix entry, say A11, and by using those constraints, we express all other entries through this A11. Or we can do it another way, and that way is more geometric, more meaningful, more elegant. So all 4 entries are expressed through, can be expressed through one parameter, which is not necessarily the same as one of the entries, but just all 4 of them are functions of one variable. Okay? So do you remember which parameter is that param in case of 2 dimensions, 2-dimensional rotations? That's of course a rotation angle, all right? A rotation angle alpha. Before returning to this point, you see, how about, okay, we expressed orthogonality of columns, normality of columns. What about orthogonality of rows and normality of rows in this case? We already have 3 constraints, so what does it mean? We need 3 more constraints that now A11 squared plus A12 squared is also equal to 1 by row. A21 squared plus A22 squared equals to 1, and they are orthogonal. A11, A21 plus A12, A22 equals to 0. What about those? If we add the extra 3 constraints, then we would have 6 constraints with only 4 entries, which means that our system of constraints is overdefined. So what do you think happens with this constraint, with this set of constraints? Any ideas?
They should be somehow connected with the first constraints.
They are satisfied automatically if the first constraints are satisfied. So the first set of constraints implies the second set of constraints. In general, we can prove it algebraically. The proof is a bit tedious, so just leave it without a proof in that case, that orthogonality and normality of columns does imply orthogonality and normality of rows. And indeed, if we now express all our parameters, all our matrix entries through one parameter, and in that case, you remember what? A11 is cosine, let's say alpha, A21 is sine alpha, A12 is, you remember what? Minus sine alpha, and A22 is cosine alpha again for rotations. Then both actual normality and orthogonality of rows and columns are satisfied. That's for rotations. A similar case would be for symmetries. Actually, this set of constraints also algebraically implies, it is possible to check just without any geometric considerations, it is possible to check algebraically, it implies that A11 A11 A22 minus A12 A21, which is obviously the determinant of our matrix A, squared equals to 1. This is again a direct algebraic consequence of those 3 equations. So this equation, determinant of A squared equals to 1, can be algebraically derived from the set of orthogonality and normality conditions, which mean that we're only left with the case of determinant A equals to plus minus 1. This parameterization, which we did, it is for rotations only. So here the determinant of our matrix A equals to +1. For symmetries, similar parameterization can be done, but we're not considering it. Okay, so we know for two-dimensional rotations, there are 4 in general matrix entries. All of them are functions of just one parameter because there are 3 constraints, and this parameter is precisely the rotation angle alpha from our geometric point of view. Now let us consider the 3-dimensional case. In the 3-dimensional case, again, let's say we'll consider 3-dimensional rotations. Symmetries can be constructed in a very easy way. You remember a symmetry is in fact a rotation and changing the direction of one of the axes. So we can consider rotation matrices and then unit matrix with a unit matrix in which, for example, one or in a 3-dimensional, or in a 3-dimensional case, all 3 axes are changed in direction. So basically, if we have a rotation matrix, let me denote it by A, and you multiply this matrix by, for example, in a 2-dimensional case, something like 1 minus 1, 0, 0, and obviously this matrix has a determinant equal to -1, correct? Then you obtain a symmetry. Or the way around, you would have -1 here or +1 here. Okay? In a 3-dimensional case, again, we consider rotations first, and then if we have, so this is a matrix for rotation, you multiply, or you can do it other way around. You can multiply it on the left with such a matrix, which means that the difference is whether you perform symmetry first and then rotation, or other way around, rotation first and then symmetry. This should be understandable. Okay, so if you take a rotation matrix and you multiply it by something like -1, for example, 1, 1, and other zeros, then this matrix again has a determinant equal to -1. You get a symmetry. If you have, so -1 can be in any row here, in the first, second, or a third. If you change the sign in your identity matrix in 2 entries, so for example, -1 here and -1 here, then the determinant is still +1, and therefore we're still in the realm of rotations. So such a transform can still be obtained by a rotation, in fact. But if you change the sign of all 3 of them, then the determinant is again -1. This is equivalent to basically swapping the directions of all your all 3 of your coordinate axes, and in that case we are in the case of a symmetry again in 3 dimensions. So the determinant is obviously -1 in that case. So yes?
What is the definition of the symmetry matrix?
The definition of a symmetry matrix, very good question. Symmetry matrix in any number of, okay, let's even say n by n, is such that it is, first of all, normal, which means that for any row I, the sum of squares, sum from j1 to n a ij squared equals to 1. Secondly, it is orthogonal, which means that for any rows ij such that I is not equal to j, the scalar product of the rows k1 to n aik jk equals to 0, which would imply those conditions that the determinant of our matrix A equals to plus minus 1. This would be an implication of this. But the third property is that the determinant of A is indeed minus 1. So these three properties, 1, 2, 3, they define a symmetry matrix. If instead of 3 we have, so this is for symmetry. If instead of 3 we have 3 star, that the determinant of A equals to plus 1, then it is a rotation. In general, these properties 1 and 2 taken alone, they imply that first of all, the columns are normal and orthogonal, not only rows. So these properties can be used interchangeably. So we can say for any j, we would have sum from I1 to n aij squared equals to 1. And for any, let's say, ij such that I is not equal to j, sum from k1 to n a ki a kj equals to 0. So equivalently, either all rows and columns are normal and orthogonal, which imply that the determinant is equal to plus minus 1. If it is minus 1, then it is a symmetry. If it is plus 1, then it is a rotation. Okay?
Okay, got it.
Great. Now let's see how many free parameters do we have for three-dimensional rotations. So we have 9 matrix entries, right? 9 matrix entries. How many normality conditions? 3 normality conditions, either taken by row or by column, but there are 3 of them. Let's say 3 columns, sum of squared entries is equal to 1 for each column. 3 orthogonality conditions. Therefore, altogether, we have 6 constraints, which means that there must be 3 free parameters in our 3-dimensional rotation. And you can imagine that if there are 3 free parameters, and these are rotations, that we can, of course, select these 3 free parameters to be arbitrary A11, A12, maybe 22 matrix elements, but that's not a very good idea. These 3 free parameters are probably what, from the geometrical point of view, what do you think they are?
Rotation around x-axis, y-axis, and z-axis, maybe.
Why not Y? Yes. There are some rotation angles. Some rotation angles, right? And indeed, because there are rotations in 3-dimensional space, there are 3 rotation angles. In 1 dimension, in 2 dimensions, only 1 angle. In 3 dimensions, 3 angles. In general, can you tell me, please, if we consider generalized n-dimensional case, how many rotation angles would we have in that case? There are n squared entries, right? So minus how many constraints? If we consider general n by n matrix, then let's say by taking orthogonality of rows and columns, we have, and normality, we have n normality conditions. And then little bit more, how many orthogonality conditions? Each row is orthogonal to other rows. So n times n minus 1. And because this relation is symmetric, then it is n times n minus 1 over 2. So indeed, if n is orthogonality conditions, if n is 2, then we have just one orthogonality condition, all right? If n is 3, then we have 3 orthogonality conditions. That's correct. So now let's see what we get. N times n minus 1 minus n halved times n minus 1. Therefore, factoring out n minus 1, it is precisely n times n minus 1 halved. Okay. That's the number of free parameters we have in the general case. So it is the same as the number of orthogonality conditions, actually. In this particular case, there are 3 free parameters. So let us construct the general rotation in a 3-dimensional space, and we will introduce these 3 rotation angles. Those 3D rotation angles are called, the 3D rotation angles are called Euler's angles. There are several ways of how they can be introduced. So we have already seen that even spherical coordinates can be introduced in several ways. So for example, counting the latitude either from the pole or from the equator, or different ways of how the longitude can be counted. So there is some freedom, which is a matter of convention in that case. Same thing for Euler's angles. There is a freedom of how they can be introduced. What I do it in a slightly non-conventional way, because typically Euler's angles are used in theoretical mechanics, because they are very important in order to specify, for example, the orientation, or we call it attitude, of a solid body in a 3-dimensional space. So, for example, before going into the general geometric case, suppose that this is an airplane. Okay, I will try to draw an airplane. Yes, an airplane. And we have the following angles which determine the attitude of this airplane. You see, first of all, the airplane has, what kind of symmetries do we have in an airplane? There is a vertical plane of symmetry, all right? So the left part and the right part are symmetrical with respect to each other, okay? Then we can draw some axes also in this vertical symmetry plane. Let's say this axis stretching from somehow the tail to the main axis of the airplane. Sorry, my hand drawing is bad here. Okay, so there is another, so that's the vertical plane of symmetry, right? There is a horizontal plane which coincides with, let's say, the main plane of the wings, right? So that's a geometric system. So, and there is a vertical axis, and let's say there is some kind of in the horizontal plane, in the plane of the wing, there is some horizontal axis as well. So how do we call them? This is of course Z. Where is X and where is Y here? To have a right hand oriented system once again. This one, is it X or Y?
X.
X, because the shortest turn from X to Y, as looking from the end of Z, must go against the clock, counterclockwise. Okay, so what are the possible rotations of an airplane? So there is a center of mass, and it can change its attitude. So first of all, it can rotate around the x-axis. A rotation around the x-axis. So basically, how is it called in mechanics? Do you know the term?
Yeah.
This is a roll. It is a rolling. When it is falling like on its side, it is a roll. Okay? It can change the direction of the x-axis. So basically, it can be like this or like this. So it rotates, in this case, around the z-axis. A rotation of a plane around the z-axis is called
yaw. I'm not sure how to read it.
Yes,
Yeah, okay.
it is called yaw. And a rotation around the y-axis. So basically, in this case, the nose of the plane is either elevated or diving. A rotation around the y-axis is called
Pitch.
pitch. Absolutely correct. So a roll, pitch, and yaw in this case. Or in Russian, for the Russian-speaking audience, a roll is called крен. Pitch is called, a very interesting Russian term, рысканье. Yaw. Oh, sorry, other way around, of course. Rotation around the z-axis, yaw, is called рысканье. Pitch is called
Tangage.
tangage. I was trying to recall the term. Yes. All right. So it is not the same as angle of attack, by the way. There is a very close term which is angle of attack, but the angle of attack is very much like pitch, but it is not related to the geometric y-axis, but it is related to basically the velocity and the velocity of the airplane relative to the air. So basically that the angle at which the incoming air is approaching the wings. And because obviously your velocity with respect to there and your main geometric axis are not necessarily the same, then pitch and the angle of attack are not exactly same. So here we're not considering any aerodynamics, we're considering only the geometric picture, and therefore it is pitch, which is not the same as angle of attack. Okay.
Excuse me.
Yes?
And if we rotate the plane, for example, in the other direction, we still have such a coordinate, so we can rename it, like, for example,
you see that these names are really connected to axes which are bound to geometric properties of a plane. So we know that the plane has a horizontal plane, which is the plane of the wings in general, and the vertical plane, which is the plane of its symmetry. And that's why our x, y, and z are defined by the geometry of the plane. Even if the plane nosedives or this plane is doing some kind of sophisticated maneuvers, then its local coordinate system is always the same, because nevertheless, even if the plane is going nose down, then it still has its local horizontal plane, which is the plane of the wings, the vertical one, which is the plane of its symmetry, and so on. That's why the names are the same, irrespective to what kind of maneuver the aircraft is performing.
Okay.
Because these axes are bound to the metal, so the metal body of the aircraft. But obviously, if you, I'm probably, maybe you meant the following. So if the aircraft performed a certain maneuver, then it would have a new local coordinate system, which is somehow connected to the old one. In this new coordinate system, it would perform then a subsequent maneuver. So for example, it did a roll, then the coordinate system changed, and then it would perform a yaw in the new coordinate system, and that way we have a composition of two maneuvers, indeed. And we have endless compositions of such maneuvers, each one represented by a certain matrix, and the whole composition of them would be represented by a product of those matrices. That's probably what you meant. Is it correct?
Okay, I got the answer on my question. Thank you.
Okay, okay. So, and indeed, we would do a similar thing for the general case. We'll introduce Euler angles, but in a slightly different way here, because there is no fixed airplane, so we don't know where its plane of symmetry or plane of wings is. We have a completely abstract setup. So in this completely abstract setup, we'll do, excuse my handwriting, we'll do the following. Again, X, Y, Z, the old system. So what we will do, we are trying to construct a very general rotation from X, Y, Z to X prime, Y prime, Z prime. So what do we do to that end? We'll do it step by step, and in doing so, you will see the advantages of matrix multiplication, of introducing our transforms in the form of matrix multiplication. So the first transform will do the following. We will do an X prime axis, which is still in the original XY, Y prime, XY plane. So X prime is here. But Y prime is now different. So we first perform a rotation in the original XY plane. We can do it actually one rotation at a time. Or what I will do two rotations at a time, and then a third rotation in a different matrix. It is just a matter of convention. So first rotation is we got X prime in the same plane XY as originally, but rotated versus X at the angle called omega. So this is similar to lambda longitude, which we did previously, right? And now we will also make an inclination or obliquity of the new coordinate system with respect to the old one. So we will have a new xy coordinate system. So y, although x prime is in the original plane, but y prime is not in the original plane anymore. It will be in a different plane, inclined one. So that's our y prime. And so this is a right angle between them. And therefore the z prime is also inclined. And the angle of inclination or angle of obliquity of the new x prime, y prime plane would be denoted by I. And therefore it is the angle between z and z prime, or denoted by I. So we have two angles as yet out of three between them. Let us in this case again construct the transformation between those planes. So again we have I vector. Do not confuse it with uppercase I, which is the obliquity angle. I, j, and k normal vectors, and then we have I prime, j prime, and k prime. So once again, new coordinate vectors in the old system. I prime is, well, I prime is easy, obviously, all right? It is still in xy plane. Therefore, for I prime, we have cosine omega, sine omega, and 0. And that's what we denote, as you remember, by A11, A1, A21, A31. Now for J prime. If we draw a line in the xy plane, which is orthogonal to x prime, then this line is a projection of J prime onto the horizontal plane, and the angle between them is I as well. Therefore, J prime is something we're doing with cosine I when we project it to xy plane, and obviously the angle between J prime and Z is a complement of I, therefore pi over 2 minus I, and therefore we immediately have its projection to Z as sine I. And here, if it is cosine I, then this line, which is a projection of J prime, is at the angle pi over 2 plus omega to x, and therefore we have minus sine omega here, and it is at the angle same omega to y, therefore we have cosine omega here. And this is A12, A22, A32. And finally, K prime is easy. Well, almost. If we continue that line, which was 90 degrees from x prime into this quadrant, then this would be a projection of k prime. Therefore, its angle with x is a complement of omega to pi over 2, and therefore we have, first of all, projections to the xy plane are sine I, obviously. If the inclination of obliquity is 0, then k prime coincides with k and has no projection to xy. Therefore, it is sine I. Therefore, it is cosine I to z. And what are the multiples here? So it is a complement pi minus 2 minus omega. Therefore, it is sine omega here. And to y, it is, what is it? It is pi over 2 plus pi over 2 minus omega. Therefore, pi minus omega. And therefore, the cosine of that is minus cosine omega. So we constructed those projections. This is A 1, 3, A 2, 3, A 3, 3. And it is easy to check. I leave it to you that obviously all those components are normal and they're indeed orthogonal to each other. So,
excuse me.
Yes.
Sorry for interrupting. I didn't get where we introduced I angle. Can you show it, please?
Oh yes, the I angle is the inclination. That's why I, or obliquity angle between this plane in which the new x prime, y prime axis lie, and the original plane, or it is the same thing as the angle between z and z prime, so it is here.
Oh, okay, I found it. Okay,
Or
thank you.
it is the same angle as here.
Okay, thank you.
So basically, as I said, there are several ways of how Euler's angles can be introduced. What I am doing here, I am using the notation which is conventionally used in theoretical astronomy. Why? Because later on, toward the end of this course, we are going to discuss a lot of astronomical examples of linear coordinate transforms and also second order curves, which are simply elliptical and other, let's say, parabolic, hyperbolic orbits of solar system bodies. And that's why the angles are introduced in the same way as it is done in astronomy. In that case, by the way, the plane x prime, y prime can be viewed as, let's say, orbital plane. Orbital plane of what? Let's say of a planet around the sun, or an artificial satellite around the Earth, and so on. So it is an orbital plane. Whereas xy, it is a standard plane. What is a standard plane? In astronomy, if we, for example, consider heliocentric movement, so planets around the sun, then this is so-called ecliptical plane, which is the Earth orbit plane. But if we consider artificial satellites moving around the Earth, then it would be Earth equator plane, in a way similar to what we did already. You remember introducing topocentric and geocentric coordinates. So the meaning of the standard plane is different depending on what kind of motion we consider. In that case, again, continuing this astronomical terminology, omega is called, it is a longitude, of a so-called ascending node. Why ascending node? Because if there is indeed some kind of orbital trajectory of our celestial body in this x prime y prime plane, then at this point, the orbital trajectory crosses the standard plane xy, and if the motion is in the positive counterclockwise direction, then here it passes from the southern hemisphere to the northern hemisphere. So this is indeed the ascending node, all right? And I is called inclination, or sometimes obliquity, although I prefer the term inclination, of the orbital plane. So in this case, we have, let us do it once again. We have our coordinate transform of old coordinates expressed through the new ones, x, y, z, are given by a matrix composed of just our columns, and therefore it is cosine omega, sine omega, and 0, then then j prime minus sine omega, cosine I, cosine omega, cosine I, and sine I, and finally sine omega, sine I, minus cosine omega, sine I, and cosine I, multiplied by the vector of new coordinates x, y, y prime, z prime. But as you see, we have introduced only two angles in this case. So now we need to do a third one. So what do you think? What is missing still? Looking at our geometric picture, so what is missing? We did the first rotation, we got x prime, then we did an inclination of the new x prime, y prime plane. So basically two angles are already in place. So what is missing?
Last rotation.
Yet another rotation, you are right. So basically one problem here is that our x prime axis is still lying in the original xy plane, whereas in fact it can be absolutely arbitrary. So in that case, let us probably change the color. In that case, we can do yet another axis now in this plane. So there would be x double prime here, and correspondingly in the same plane there would be a rotated y double prime, whereas z remain the same for them. So z prime and z double prime remain the same. So there would be yet another rotation now in the new plane at some angle, which is typically denoted by omega lowercase. And this angle, again, in astronomy, typically corresponds to the angular rotation to the direction of the shortest approach point of the trajectory. So this is, for example, so-called pericenter, although it is not completely clear here, but let us assume that in this point, the body, for example, a planet or a satellite, is at the shortest distance to the center. Then omega lowercase is a so-called longitude over pericenter. And then it is very easy to construct the remaining transform because it is only two-dimensional, and it is very easy to do it in the new coordinate system. So now what we do, we express x prime, y prime, z prime via the coordinates x double prime, y double prime, z double prime. Okay, z axis is the same, so rotation happens only in x prime, y prime plane. So because they are the same, it is 0, 0, 1, and they do not affect z double prime doesn't affect transformations here. And for the remaining 2 by 2 matrix block, it is just a normal rotation at the angle which we called alpha. Now it is called omega lowercase. So it is cosine, sorry, not alpha, cosine omega minus sine omega, sine omega, and cosine omega. So, and now, if we want the all-through transform, so suppose that this matrix is A1, this matrix is A2, A1 depends on omega and I, and A2 depends on omega lowercase only, then the overall transform x, y, z, in which old coordinates are expressed through the new ones, is given by a certain matrix, which would be too tedious to construct explicitly. X prime, x double prime, y double prime, z prime. Let us denote this matrix by A, which depends on all omega I and omega lowercase. And obviously, by substituting one equation into another, you see that it is simply a product of A1 omega I times A2 of omega in this order, obviously. As a very easy home exercise, I suggest that you do this matrix multiplication and you obtain the actual entries of our matrix A. But so in this case, indeed, we have a general rotation. A is a general rotation matrix. Which is parameterized by 3 angles, okay? And from the computational point of view, it is very advantageous actually to keep your matrices simple and to construct, for example, this A1 and A2, and then to multiply them when it becomes necessary. It is much easier than every time recompute the entries of, let's say, a large matrix A. Any questions here?
What was the name of the new angle?
Oh yes, you are right. The name of the new angle, omega lowercase, is called argument of the pericenter. So the longitude of ascending node, inclination, and argument of the pericenter. We will use them very extensively in the future. For the moment, let's make a very, very, very short break, and we'll continue from that point on. Okay. Okay, going back to our lecture, some important points. You have already seen, I believe, in your tutorials that linear transformations do not really need to be orthogonal and normal. There are many more transforms. So there is a general transform in which our matrix A could be an almost arbitrary matrix, all right? So general linear transform in a similar way, our old coordinates x, y, z are given by some matrix A times new coordinates x, y, y prime, z prime, where A is any, but there is one very important condition. Do you remember what? It doesn't need to be in the general case, it doesn't need to be orthogonal or normal. But there is some very important condition imposed on A. Do you remember which condition?
Non-zero.
Non-degenerate. The determinant of this matrix A must not be equal to 0. So which is called non-singular or non-degenerate matrix. Why is it important? Because if and only if this matrix is non-singular, then for any x prime, y prime, z prime, we can express it back through xy as inverse of A times xyz. And in this case, you really need to compute the inverse. So in the general case, the inverse is not the same as a transposed matrix. In the orthogonal and normal cases, both actually symmetries and rotations, constructing the inverse is very easy, as we have seen. Just transpose the matrix. In the general case, it is not. And again, in the general case, this matrix A can be written as A11 and A21, A31, and this is the next, I would say, I wouldn't call them ijk prime anymore. This is some kind of A vector. This is A12, A22, A32, B vector, and this is A13, A23, A33. This is called a C vector, and then this means that A, B, and C is a new basis, such that any geometric vector, let's say V, which is originally expressed as x times I plus y times j plus zk, is also expressed as, tell me please, so how is it expressed, y, a, b, c?
Y x prime times A, Y prime times B, and Z prime times C.
Yes, plus z prime c. Whereas x prime, y prime, and z prime are not Cartesian coordinates anymore, because A, B, and C do not really need to be orthogonal and normal. They make a basis, which means that they are linearly independent. So A, B, C, linearly independent What does it mean? Linearly independent, I believe you have seen it in your tutorials already. It means that there do not exist such constants alpha, beta, and gamma, which are not so that they are not all zero. So alpha squared, let's say, plus beta squared plus gamma squared is not equal to 0, such that alpha A plus beta B plus gamma C equals to a 0 vector. Should denote 0 with a arrow, or we can denote it by theta. You remember our original notation from the first lecture. So linearly, vectors are linearly dependent by definition if there exist constants alpha, beta, gamma, not all 0 together, such that a linear combination of these vectors with coefficients alpha, beta, gamma is 0. If such constants do not exist, so the vectors are not linearly dependent, they are called linearly independent. That's why negation in front of the existential quantifier, all right? There do not exist alpha, beta, gamma not identically equal to 0, such that a linear combination of vectors with these coefficients would be 0. Okay? And linear independence of A, B, and C is equivalent to determinant of our matrix A being which? Not 0. The determinant of our matrix A composed of these vectors as columns, or rows, but we use columns here. The determinant would be 0 if and only if the vectors are linearly dependent. So this is our genericity condition, which say that three vectors A, B, and C form a basis. They are not linearly dependent. And if they are not linearly dependent, then we can use a matrix composed of those vectors as columns for a linear transform. Okay? Okay. Now what? What do you think is the geometric meaning of dependence and independence? So if let's say A, B, and C are non-trivial vectors, so let's say none of them is 0 by itself, what does it mean that such a linear combination which makes them 0 exists or does not exist? Any intuition on that?
If they don't
all
belong
them,
to one plane.
Yes,
yeah.
coplanar it is called. You are right. So if such a linear combination exists, this means that the vectors are coplanar. So, for example, if A, B, and C are all, let's say that's the plane of A and B, but C is not in this plane, then they are not coplanar, linearly independent, and the determinant of A is not equal to 0. But if vector C lies in the same plane, then they are coplanar, linearly dependent, and determinant of A is equal to 0. Please note, obviously, that if A, B, and C, this set of vectors, contains a 0 vector by itself, so for example, C is 0 by itself, then such a system is always linearly dependent. It is linearly dependent simply because you can select alpha and beta being, for example, 0, but gamma equal to 1, and we still get 0 linear combination. So all conditions are satisfied. So 0, 0, 1 mean that coefficients are not all identical 0. Nevertheless, we get a 0 linear combination with a 0 vector. So if a system of vectors contains a 0 vector, then such a system is always linearly dependent, and we can say that a 0 vector is coplanar because it is 0 with any other 2 vectors. The other 2 vectors form a plane, and the 0 vector naturally belongs to this plane because it is 0. Is it clear?
Yes.
Okay. So if we take then in this matrix A, any entry, Aij, so what is actually Aij? Returning to this equation of how our vector is decomposed, you can say that multiplying, let's say, the left-hand side and the right-hand side dot product with I, we get x, let's say, in the left-hand side, and then we get scalar products of A with respect to A, B, and C with respect to I, and so on. So basically, these are obviously projections of, for example, A12, A22, A32 are projections of the vector B onto the corresponding axis of the original system. So we can say that in general, because we have different notations here. Okay, so for example, AI1 for the first column are projections of A to X, A to Y, A to Z. A row is varying here, I is 1, 2, 3, 1 in the column 1. In a similar way, AI2 are projections of B to X, B to Y, and B to Z. And AI3 are projections of C to X, C to Y, and C to Z. These projections are no longer in general normal. So we can't say that the length ax squared plus ay squared plus az squared is equal to 1. They are no longer normal, orthogonal to each other anymore. But as long as the determinant of A matrix composed of those columns is not 0, we can use ABC as a new basis, and we can define a general linear transform this way. In our geometric applications, in fact, we would not need such transformations very often. Mostly we will be working with orthogonal and normal transformations, mostly even with rotations and sometimes with symmetries. But in many problems which you would encounter in let's say physics and engineering anymore in the future, it will be important to use the general linear transforms as well. So for example, a physical situation, just not a mathematical abstraction, but a physical situation when this does actually happen, and this is important, is the physics of crystals. So a crystal may have some physical, let's say, angles or directions of, I wouldn't say symmetry, but they are called principal stress directions, which are not orthogonal to each other. So there could be some ABC non-orthogonal physically defined vectors, which mean that, for example, splitting the crystal by applying force to it would be easiest if the force is applied in either of those directions A, B, C, which are not orthogonal, not completely orthogonal to each other. Or optical conductivity of a crystal would be at the maximum along those three axes, which are again not necessarily orthogonal to each other. Okay. Now for today's lecture, we will consider the final and a very important concept, which you have probably seen already, maybe you have seen, maybe not, in your tutorials, which is the vector product of vectors, or cross product. Cross product or vector product of vectors. Let us consider the following problem. Suppose that we have two given vectors A, which are given by its components AX, AY, AZ in the original XYZ coordinate system, and B also given by BX, BY, and BZ. Geometrically, we already know that if these two vectors are not collinear, suppose that they're not collinear means that A is not a certain multiple lambda times B. How do we, using what we already know, how do we express in some other way this property that A and B are not collinear?
If they is not the same line.
Collinear means the angle between the vectors would be what?
Not zero.
Well, if lambda is positive, then the angle between them is 0. But if lambda is negative, then the angle is pi over 2. Is
Yes.
equal to pi. So, which means that the angle is not 0 or pi, which means that the cosine of the angle between A and B is not equal to plus minus 1, which means that the scalar product of A times B divided by the length of A and the length of B is not equal to plus minus 1, which means that A times B squared is not equal to absolute value of A squared times, all of them are equivalent statements, obviously, B squared, which means that AX BX plus AY BY plus AZ BZ squared is not equal to AX squared plus AY squared plus AZ squared times BX squared plus BY squared plus BZ squared. So that's what we mean non-collinear, actually. Okay. So
excuse me, in fraction you lost non-equal. You wrote
you're
equal.
absolutely right. Non-equal to, you're right. Non-equal to plus minus 1. Thank you for pointing it out. And suppose that, yes, so we have these two vectors which are not collinear. By the way, this immediately means that A and B are not 0. So you already know from the geometric consideration that they define a certain plane. So we would like to construct a vector which is orthogonal to that plane given by A and B. So it would be orthogonal to both, actually, A and B, some new vector C. which is orthogonal to B, and which is orthogonal to A, and therefore it is orthogonal to the plane AB. How do we do that? Well, we can, A and B by themselves may or may not be orthogonal to each other. What is important is that they are not collinear. Because if they are collinear, then the plane is not uniquely defined, as you can see from elementary geometry. And then we can obviously construct a C, which is orthogonal to collinear A and B, but this C is not uniquely defined in that case, even up to a multiple. So how do we solve this? We can construct a system of equations. If C is orthogonal to both A and B, then we have, so suppose that C is Cx, Cy, Cz. We'll finish a little bit late today because we started later. Then Cx, and we know that we must have dot product Ca equal to 0 and Cb equal to 0. Cx Ax plus Cy Ay plus Cz Az, where Ax, Ay, Az are known, but Cx, Cy, Cz are not known, equals to 0. Cx Bx plus Cy By plus Cz Bz equals to 0. So we have a system of two equations with three unknowns, right? Which is a so-called undefined system. So if a solution to this system exists, then it is not unique. And you can immediately see why is it not unique. So suppose that we found a solution, a certain solution, Cx, Cy, Cz. Then how can we construct other solutions to this system?
Multiplied by -1.
Multiplied by any lambda, including -1. Because the system is homogeneous. We have zeros in the right-hand side, and therefore if a certain solution Cx, Cy, Cz is found, then lambda Cx, lambda Cy, lambda Cz would be a solution as well. That's number one. Number two, I said if a solution exists. Well, some solution always exists. For example, we can take C a zero vector, but that's not interesting. So another condition would be that C must not be a zero vector, provided that our A and B are not zero as well, because otherwise we have a trivial solution only. And actually what we can do, we can solve this system. And we can show that the following vector C is a solution. Just by substituting it into our system, we'll see that yes, it satisfies it satisfies all requirements. So suppose that okay, C is a Cx, Cy, Cz, where the components are given in the following way. Cx is composed of actually A and B components with respect to Y and Z. It is A, Y, B, Z minus A, Z, B, Y. So if you look at this part, you can see that it is like a determinant of the matrix A, Y, A, Z, B, Y, B, Z. Cy is, now we consider X and Z, but this would be other way around. AZ bx minus AX bz. And finally, CZ is AY, sorry, AX by minus AY bx. Look at each column in the obtained expression. We have a permutation of y, z, and x, so the indices never repeat. Y, z, x, z, x, y, z, x, y, y, z, x. Okay? A vector defined in such a way is called a cross product or a vector product of the vector A and B. This is a definition of cross product and written with a cross. It is indeed orthogonal to both A and B, as you can check by simply substituting those expressions into our equation. So you would indeed have zeros. Obviously, if we defined a vector C that way, then a vector lambda C would be a solution as well. So this vector is defined only up to a multiple. But for the cross product itself, if you compute the absolute value of C, then you can see it for an exercise that it is a product of absolute values A and B times this, in this case, it is not cosine, but sine of the angle between A and B.
Excuse me, is that area of parallelogram built on vectors?
It is. Geometrically, you are absolutely right. If we build a parallelogram on our vectors A and B, then vector C, from the geometric point of view, this can be proved by simply, well, from this it is obvious. It is A times B times sinus of angle between them. Then half of that is the area of triangle built on A and B, and the whole product with coefficient 1 is indeed the area of the parallelogram. You're absolutely right. Built on A and B, and this is C. So C is orthogonal to both A and B. Moreover, in this case, geometrically, because C is, so for example, this is angle phi between A and B. Therefore, this is simply AB, where A and B are absolute values, sine phi. And geometrically, C is pointing toward that direction relative to the plane AB, that the shortest rotation, again, from A and B, looking from the end of C, is counterclockwise. So immediately applying this to what we know about our original coordinate system, x, y, z, with I, j, k normal vectors, I, j, and k, we can say that I times j is equal to what?
0?
A
No.
divided by
It's 1.
Cross product, yes, length is 1, and the cross product is a vector. As we say, it is precisely as we should construct it here. It is a vector orthogonal to the plane made by A and B, and such that the shortest rotation from A to B is counterclockwise from looking from the end of the vector C. So comparing this picture and this picture, here we have A, B, C. Here we have I, J, and what? Okay, just constructively, I is a vector 1, 0, 0. J is a vector 0, 1, 0. Okay? So in this case, I times j equals to, if you really compute this, you will find that this is 0, 0, 1. I times j is simply k. Please have a look. Is it clear or not? It is orthogonal to the plane of I and j. The absolute value of this vector is 1, because the sinus of ij is obviously 1. It is 90 degrees between them. And it is looking in the direction such that the shortest term between I and j is counterclockwise. So I times j is k. Now we are looking from now the positive end of I. J times k is I. Okay, we are now looking from the positive direction of j. Therefore, k times I, rotating this way, k times I is j. And in general, A times B is anti-commutative. It is minus B times A. Why? Because swapping A and B in these expressions does indeed change the sign of the result. Okay, what I suggest we do, we stop here at the moment. Please look carefully at how we have introduced our vector product of vectors, and play with normal vectors I, j, k. And this will be very useful for us next time when we introduce straight lines and planes in our coordinate system. By the way, yet another application of the vector product is the following. You remember when defining coordinate transforms, we constructed those formulas, first for I prime, then for j prime, then for k prime. Actually, it is sufficient to do so for only two vectors. If you constructed, for example, already formulas for I prime and j prime, and you know that I prime, j prime, k prime is a right-handed orthogonal normal system, then obviously you can simply compute k prime by computing the cross product I prime, j prime. Or it might be useful to derive k prime explicitly. In that case, you can verify that this orthogonality and normality conditions hold. Okay?
Can you explain one more time how you got the equation for C, the solution of like this matrix, right? Yeah, this one.
You can do it by solving this system explicitly. I didn't do it. I just wrote a solution. But what I suggest, you can simply substitute this into the original system of equations and see that the equations are identically satisfied.
Okay, so it's just a solution of the system.
It is just a solution of the linear system, yes. And obviously, there is a whole family of solutions, because if this is a solution, that lambda c for any lambda is also a solution. But this solution is good because it doesn't have any divisions. Normally, when we solve systems of linear equations, we divide by a certain denominator, right? but this solution doesn't contain any divisions. That's why this solution would generically be okay, even if the genericity conditions which were originally imposed are not satisfied anymore. So suppose that if A is 0 or B is 0, or they are not 0 but collinear, then this solution for C would still stand. So this solution is valid even in degenerate cases. We first constructed under the genericity assumptions, but it is also valid in degenerate cases. That's why it is nice. Okay.
Okay, thank you.
Okay, well done for today. Thank you very much indeed. And shortly afterwards, when our video is compressed, then uploaded to YouTube, and then accepted by YouTube, you know that it takes a while, you will see everything in Moodle and in YouTube. Thank you.
Thank you, goodbye.
Thank you, goodbye.
Thank you, goodbye.